So we today are going to talk about the last of our tests for convergence, and then go on to, well, time permitted, I don't know if we have enough time, but then we're going to start talking about power series, which is kind of like our final main topic. You know, the semester is getting close to over. I think we only have 6 more class meetings, ordinary class meetings. We have, you know, the last day of class is our last of the tests, like your last chance to check things off of the checklist. And then, of course, we also have the final exam, which is its own thing, not related to the checklist. Anybody got any end times questions? Yeah.
What's the final exam like?
The final exam, it will be like the quiz questions, but it's, you know, the quiz questions, it's like once you get it right once, you never have to do it again. But you do on the final exam. So the final exam is just kind of like, it's meant to cover everything, although I'm not actually going to put everything on it, but anything goes on the final, yeah.
So are you saying it's going to be similar to the midterm where it's like one question for each topic, or it's going to be like not like that at all?
It probably will not be one for each topic just because that would be too long. And it will also be, it will be graded in a more ordinary way. Like each question might be out of 10 points and I'll give you like partial credit on it. Unlike our quizzes are, you know, out of 3 points, yeah.
So if for the last class test we get one of the quiz questions wrong, there's like no chance to come pick it up?
It's over, yeah, right. Yes, the question was, if you still haven't gotten one of your check marks by the last class, that was your last chance. Although, I mean, like I said at the beginning, I hope that everybody remembers, you have to get at least 2 points on all of the deal breaker questions. Although, if you still haven't gotten one of the deal breaker questions, I am going to be very generous about like letting you try again every day, and this may even continue after the last day of class. But basically, under ordinary circumstances, the last day of class is going to be your last chance to get those checks on the big list. Everybody, of course, can try another question once every 2 weeks, and so I might let you do one of those after the last day of class, but not more than that. Yeah.
So are only grades the quiz grades and the homework grades right now?
That's right. Yeah.
Okay.
Yeah, and then the final exam will also get averaged into that at some. The syllabus says how much each of those 3 things is worth. I don't remember off the top of my head. All right, great. Continue to come and try again the old questions. All right, let's talk about the ratio test then. I wrote down the basic rule last time. I will just write it once more. It says, so for a series, we call this L. L is the limit n goes to infinity of an plus 1 divided by an. It's called the ratio test because it's about that ratio. And this is the ratio of, you know, one term divided by the one that comes before it. And in a geometric series, this we call R, and a geometric series means that these ratios are always equal, and so you don't even need to talk about the limit. They're just all the same number. But in a series which is not a geometric series, these ratios will not all be the same number, but you can still take the lim as n goes to infinity. And the basic idea here, the ratio test basically says that L acts like R. I'm sorry, I meant to write, I forgot to do this last time, and I forgot again this time. There needs to be absolute values in here. Sorry, I forgot. Absolute values are sometimes annoying to deal with, but actually in here they're good, and we'll do some examples. You'll see why. But anyway, the ratio test says if the L is greater than 1, then the series actually the series AN is absolutely convergent. That means it converges, and furthermore, even if you took the absolute values of all the terms, it would still converge, all right? This is what I mean when I say, informally speaking, L acts like R. Like if you can remember the rules about the R, if R is bigger than 1, then sorry, I meant to say less than 1 here. This is the opposite of R, right? Greater than 1 means it diverges. Sorry about that. Less than 1. All right, it's like R, right? When R in absolute value is less than 1, it converges. Now I didn't put an absolute value here because the absolute values are built in, the L sort of already has the absolute values in it. All right. Also like R, if the L is greater than 1, it diverges. Then this diverges. I didn't write the 1. If L is greater than 1, then it diverges. And this is kind of like the bad news. If L equals 1, you don't know if it converges or not. So if the L equals 1, the ratio test is inconclusive. All right. So unfortunately, this is unlike R because, if R equals 1, it diverges. The rule for R is if the R is less than 1, it converges. If it's greater or equal to 1, then it diverges. This is not so in the ratio test. It's because if this L is a limit of various ratios, and if the L equals 1, it might be because all of these fractions are less than 1, but then in the limit they become 1. And if they were all less than 1, then actually it might converge. But if this limit equals 1, it could also be that they were all greater than 1 and approach 1 sort of from above, and in that case it would diverge. So if the limit equals 1, you really don't know. And if that really happens in an example that you care about, you have to just use one of our other methods. But the big advantage to the ratio test is there are no assumptions on the series, unlike our other tests, like the integral. It must be decreasing terms, and the comparison test, they must all be positive. Nothing like that needs to be the case for the ratio test. So it's super powerful in my opinion. Let's just do some examples. Most of the examples that we have done in the other sections, you can also do using the ratio test. Let's try this one. Does it converge is the usual question. All right, let's not think too hard about this. You can go straight into this limit. L, it's the lim absolute value an plus 1 divided by an, right? And as usual, I'm going to write an, dividing by an as a reciprocal, multiplying the reciprocal, right? Just like I do when I'm doing a limit comparison test. We do have absolute values around everything, but let's write an plus 1. So here's how I'm going to do this. You may not have to write this step. An plus 1 plus times the reciprocal of an, right? That's how I'm going to do this. So an plus 1, you have to be a little bit careful, but that means you plug in n plus 1 instead of n in the definition of the series, in the terms, the tweens. Make sure the plus 1 is inside the exponent on the bottom there. That's different from 2 to the n plus 1. Okay, and then I'm going to write times the reciprocal of an, and that would be 2 to the n up top and n on the bottom. All right? And now we have to take the lim of this thing, which is, I suppose, a slightly complicated thing, although we can usually simplify. And in order to simplify this, first of all, I will say everything that I see here is positive, and so the absolute values don't do anything, right? We can just forget the absolute values because everything inside here is a positive number. N is positive, so n plus 1 is positive, so 2 to the n is positive. Everything here is positive. So the absolute values in this problem are irrelevant, and I am going to, for the sake of simplifying stuff, sort of like move them around so that the similar type things are grouped together. All right. And now I need to do this lim, but the first part of the lim is a ratio of polynomials. So you can do the old divide by the biggest power trick on this. And then, anyone have a suggestion about 2 to the n over 2 to the n plus 1? Yeah?
You take away 2 to the n on both, and then just keep a 2 on the bottom.
Yeah. This can just like simplify, right? You can subtract the exponents here. I have 2 to the n, like n factors of 2 up top, and then n plus 1 2's on the bottom. So we cancel all except one of them. So this I'll just write one more step before we do the lim. That thing over there is just a half. So we don't even, sorry, there should be a 2 under that. I meant n plus 1 over n, right? And this here, 1/2, we don't even really have to think about that when we take the limit, all right? So we just handle this limit in the way we usually do, which would be to divide through by n. So this is a 1 plus a 1 over n, and then I have, over 1, right? I divided everything through by n. Times a half, and then we take the limit. And the 1 over n goes away, and everything else stays like it is. So it's going to be 1 plus 0 over 1 times a half. That first fraction is just 1 over 1, which is 1. So this is all just a half. All right. So L is less than 1, which means it converges absolutely. So the sum n over 2 to the n converges. Now the question, specifically what I asked is just, does it converge? The answer is yes, it does converge. In fact, the ratio test says actually it is absolutely convergent, which is it's even stronger than just ordinary converge. But I didn't really ask you that, but it converges absolutely if you care. But as for does it converge or not, yes, it does. All right. Any thoughts about that one? This is the ratio test. It goes pretty nicely. I got one other, and then I have one for you to try. I think I said last time, I kind of like the ratio test. I'm a ratio test guy myself. Says that in my Tinder. No, it doesn't. I don't have a Tinder. I got out of the game before Tinder came along. And I'm hoping to never get back into the game. That game is not for me, folks. I'm enjoying the game I got. You know what I'm saying? Anyway, this is the, I'm going to do the ratio test on this. All right. Now, and as I mentioned before, like some people don't like the absolute values, but actually the absolute values help a lot when you're doing problems like this. So let's do the ratio test here. Something I like about the ratio test is you don't really have to sort of stop and think before doing it. And there is no step at which I wonder, all right, what am I supposed to do now? Which that actually is a large part of what makes the dealing with series difficult. But it's the ratio test is a fairly straightforward calculation, right? So I have to put the absolute values, and then inside the absolute values, I first am going to write a n plus 1, which means putting n plus 1s instead of n's everywhere. So that's a n plus 1. And then times the reciprocal of a n, right? It's a n plus 1 divided by a n, which is easier to say. A n plus 1 times reciprocal of a n. So that's, I'm writing the terms as given, only I'm putting upside down. That's the reciprocal. All right. She didn't like my Tinder joke. Okay, and let's do the limit. This looks kind of crazy, but again, I'm going to sort of move stuff around to put similar things together. So I'm going to let's put the minus 1 to the n's all together. I still have these absolute values around everything, but minus 1 to the n plus 1 over minus 1 to the n. I'll put the e's together, e to the n plus 1 over e to the n, and then I'll put the n's together, n to the 8 over n plus 1 to the 8, like that, all right? And now, can we simplify anything here? Yes, we can. So those e's, they actually are like the 2's were in the previous example, right? I had 2 to the n plus 1 over 2 to the n, or some, it was upside down. But what's left over when we simplify these e's? Yeah, just e. Yeah, there's like one extra e on top, so you cancel them all, and you end up with just e. What about this right here? Actually, they can cancel too, and you just get minus 1 There's like one extra minus 1 on the top. But actually, I'm not even going to go there because these absolute values, the effect of them is just to kill this thing entirely. Because all this is, it's either -1 or a +1. And when you take the absolute value of it, it becomes a 1. And so, and everything else that I see is positive. So this actually, I'm going to say is, I'm just gonna forget about this entirely because it's all it is just a +1 or a -1, but it's inside of an absolute value anyway, so it's gonna go away. From here, all I have is just E. And then the last one, it's not so simple to cancel in the last one. Of course, you could do a ridiculous FOIL on the bottom, but I wouldn't suggest it. What I would suggest is a cute little trick like this. N over n plus 1, the whole thing to the 8. This kind of thing happens often when you're doing the ratio test, so you will find yourself doing that fairly often. All right? And then we can just do the lim inside of the 8th power. So I would do my usual, divide the top and the bottom by n. I'm doing everything just like inside of the 8th power. And so this is lim e, and then 1 over 1 plus 1 over n to the 8. And then we can take the limit, and that little 1 over n becomes 0, and everything else stays like it is. So I get e times 1 over 1 plus 0 to the 8. And that, inside those parentheses, is just 1. And so 1 to the 8 is, again, just 1. So my whole answer is E. All right. So L is E. Anybody happen to know? Is that bigger or 1? Bigger than 1 or less than 1? It is bigger than 1. I hope everybody knows. E, I don't care if you know the digits of E, but it's like 2 point something. That's all I know. It's between 2 and 3. So that means L is bigger than 1, so it diverges. All right, this is the ratio test. You don't have to have a lot of big ideas. Yeah?
For the step on the top, can you just see that the highest power will be 8, and then it'll be multiplied by 8, so you can just do the coefficient?
Yeah, you could imagine what would happen if I did the ridiculous FOIL here. Would be I'd get degree 8 polynomials on the top and on the bottom. Yeah, and so if you want to think of it that way, that's fine. Then the
not to show all the work for that, just kind of write like the coefficient.
yeah, sure, right. Yeah, if they are, this is a fact. If the two polynomials have the same degree, then the limit is equal to the ratio of the leading coefficients, which would both be 1 in this case. So you will get 1 over 1. That's fine if you want to use that. That's a little shortcut, I suppose. All right. You will have to be a little bit careful if, well, yeah, that's fine. I got one for you to try, and then see what you think. And then we'll talk about some other stuff. Does it converge or not? Use the ratio test. See how you like it.
This is all. This goes out. No. But you gotta do times plus 1, 5n plus 1. You do the reciprocal, which is 5n over n.
Can we talk about these? It looked like people got started well and finished off well too. This is what you get if you just plug everything in. You have to put the plus 1 term here and then times the reciprocal of the original term. It should look like that. And now I'm going to combine, sort of put the similar things together. At some point, you will hope to ignore the absolute value signs. Can I just throw the absolute value signs immediately away? I think we can. Everything on the inside there is all positive. I don't see any negative anythings. So this is all positive, so I don't even care about the absolute values at all. So I can put the ins first, and then the 2s, and then the 5s. Make sure you get them the right way around. I just rearrange stuff. And then the 2s and the 5s, you don't need to take the limit because they will actually cancel. The 2s cancel, leaving 1, 2 on the top. So I do have this, which I'll have to do the limit of. But the 2s cancel, giving me a 2 on the top, and the 5s cancel, leaving me a 5 on the bottom. So it's like that. And then what is that limit? It's going to be 1. I mean, the n plus 1 over n becomes a 1 when you do. I will change that to a 1 plus 1 over n divided by 1 times 2/5. And then this becomes just 2/5 in the limit. That 1 over n becomes 0. And so that fraction is just a 1. All right? 2/5 being less than 1 means it converges absolutely. So L is less than 1, so it converges. All right, great. Any thoughts about that? Questions? Great. I thought we should maybe discuss at least one example where it doesn't work, like this, the third case, L equals 1. Actually, that can happen, and it can happen in fairly ordinary examples. So the L equal 1 does occur, and it will happen in cases when the thing looks like a p-series. So for example, what about something like 1 over n cubed plus 1? Now this one converges. This is fairly easy to deal with using the comparison test. I would compare this being, if I were using the comparison test, I would write this is less than 1 over n cubed because this denominator is bigger than that. But then this converges, which means this converges because it's smaller. So this one is easy to do using the comparison test, but actually it's hard to do with or it just doesn't work at all to do with the ratio test. So let's just see what happens. If we try the ratio test, I would say this L is the lim. The absolute value is not going to matter, but you ought to write it at least for the first step. N plus 1 first. So that's this, and then times 1 over an, which would look like this. So this is the lim. All right, everything's positive, so I don't need the absolute values, but it will say n cubed plus 1 over n plus 1 cubed plus 1, all right? And now you could do the FOIL on the bottom, or you could be like our friend Aaron and just say this is a ratio of 2 degree 3 polynomials. And so the limit will equal the coefficients on the degree 3 term, which is a 1 and a 1, all right? Or if you like, you could do the FOIL. It's not so hard to do the FOIL on the bottom. If you remember your Pascal's triangle, this will be n cubed plus 3, n squared plus 3, n plus 2. It's 2 because there was another 1 over here. But anyway, This is a degree 3 on the top and on the bottom. And the leading coefficients are 1 each time. So this limit is a 1. All right. And what's our conclusion? There is no conclusion. So L equals 1, which means I would say the ratio test failed. So do something else. All right. So if this was on our quizzes, there's going to be a question that you already know is about the ratio test. So I'm not going to make this happen on the quiz. Although I might say, use the ratio test to say if it converges or diverges, or tell me if the ratio test fails. But on the final exam, I might just for fun give you one like this and not tell you which method to use. And so if this happens, it means you should have done it some other way. And in this case, the other way you should have done is the comparison test. Yeah.
So if something is convergent but not absolutely convergent, the ratio test fails.
That's right. Yeah. Yeah. Yes, this is a good observation. The ratio test always, when it succeeds, it only tells you about absolutely convergent. So something which is convergent but not absolutely convergent will always be in this category. That is what we call conditionally convergent. Yeah. All right. Great. That's really all I wanted to say about the ratio test. It's a fairly, somewhat weird, but at least fairly straightforward calculation. You just find that limit, and you don't have to think very creatively about it. You just have to do the limit. There is one more test which is very similar to the ratio test, and which is why on our big checklist I actually put them together, and in our book they are in the same chapter or the same section of the book. This is very similar. It's called the root test. The root test. I will just write down what the test says as a theorem, and then I'll say a few words to explain why this is true. It's very similar to the ratio test. So this is called the root test. And here's what it says. It says, again, this works for any series. It involves an L. It's a different L, though. The lim n goes to infinity. This is a very weird limit. The lim of the nth root of absolute value an. All right? If it's up to me, I usually don't want to do it this way because I don't like dealing with nth root, especially in a lim as n goes to infinity. This strikes me as very weird. But there are actually many examples where this is a very natural way to do it, and we'll see why. But anyway, this also is like R, and so the conclusions are all the same as before. If L is less than 1, then the series AN is absolutely convergent. If L is greater than 1, then the series AN diverges. And again, L equals 1 is inconclusive. This is the root test. All right. This is the idea. Well, this is not the idea. This is what it actually says. Now, I will, this is, in practice, to use this is just like using the ratio test. Although, maybe I'll say a few words about why you should believe this. The idea here, I'll put the idea in blue. The idea is L is this weird lim, the nth root of AN. Now, what that means, I will say, i.e., this kind of means that AN is basically like L to the power n. When n is large, I'll put approximately. When n is really big, this saying L is the nth root of AN is the same as saying AN is L to the power of n. Because if you solve this for L, you get that nth root, right? I'm not writing the absolute values. I'm just being vague at this point. This means that AN is something like L to the power n. And this means if you do the ratio test, so a n plus 1 divided by a n is something like L to the n plus 1 divided by L to the n, and that cancels out and you just get L, all right? So the moral of the story is this L is basically the same as this L. And so all the same rules about this L in this weird root version, it's really the same thing as this ratio version. And so all the same rules still apply. Although this is just it's a much weirder thing. It's a much weirder thing to write, but this L actually acts from an abstract point of view. It's more or less the same as the ratio that we were talking about in the ratio test. All right. The question that may be on your mind is, why would I ever want to do it this way? So I will say, use the root test on nth powers of things. So actually, some of the examples we've already done, you could have done with the root test and it would have worked great. Use the root test, generally speaking, on nth powers of things, and I will say especially, this is where the root test is really necessary when n is inside an nth power. In those cases, you really kind of need the root test. So let's try one like that. N plus 1 over 2n to the power n. All right? You can have n inside of an nth power. This, for real valued functions, you basically don't talk about things like that. Like you can write down something like, 3x to the power x, but actually there are abstract reasons why this is not always well defined. A thing to the power x is only well defined when that thing down here is a number, positive number, like greater than 1. If you allow the thing on the inside to also be a variable, this you can write it down, but it's very weird and strangely behaved from the point of view of calculus. But there's no problem with this though, because n is always a whole number. None of the weirdness can occur. Anyway, what are we going to do? Let's just do the root test. So I'm going to do the root test. It says L is lim n goes to infinity, nth root of absolute value n plus 1 over 2n to the n. I have parentheses and then absolute value. All right. First of all, the absolute value doesn't do anything here because it's all positive. So I'm going to throw away the absolute value. And what remains is nth root n plus 1 over 2n to the n. And can we simplify this? The answer is yes. Anybody see what this does simplify? Yeah?
The power of n's, it cancels out, so you just get what's inside the root.
Yeah, the nth root cancels the power of n. This is kind of like having a square root with a squared on the inside. They cancel. Here we have an nth root with a power of n on the inside. So I get just lim n plus 1 over 2n. And now this is an easy limit to do. All right. So this is, when I see something like this with an n in the exponent and also n's in here, I would immediately think I should do the root test to kill this n. That's what the root does. It gets rid of the outer nth power. All right. And what's this lim? This lim is a half. You could divide the n's as we usually do. I get 1 plus 1 over n over 2, right? And then n going to infinity makes that 1 over n go to 0, and I get a half. So what's my conclusion? This being less than 1 means it converges, absolutely. So L is less than 1, so it converges. That's that. All right. The root test, it works very well in the situations when you want to use it. If there's no n exponent, you basically should not do the root test in those cases. This thing will be too complicated. Oops, this thing. All right, I have 3 more for you to try, and I'm going to leave it up to you. Each time you can decide to do the ratio or the root. In my opinion, one of these you should definitely do the ratio, one of them you should definitely do the root, and the other one actually you could do either way and it'll work either way. So I will leave it to you to decide which will be appropriate for each. One of them you really should use the root. One of them you really should use the ratio, and the other one you could do either way. See what you think.
So wait, this is pretty.
Right, cause that one wasn't right on top.
Or is it just like one? Or is it Oh yeah, I keep doing. Yeah. Wait, so that's right. So that's cool. This is not great. Then you don't need that.
I should like
Yeah, like that. So you limit it to the end, to the end, like inside to the end.
Yeah.
It's gonna be paired with two. Still there? Three to the paired with wait. No, it's like
yeah, like we're talking.
so you can see here, right? I got the same area. Yeah. Right? I paired two to the end. So okay, then I multiply that by the 3 over 3, right? And then you add plus that with everything. And then you solve it. So right now, you don't correct that. No, all you gotta do is pair by pair.
Still good here? You guys still good here? All right. You doing the ratio test?
Yeah. Am I not supposed to? Do you remember?
This is what I said. N is in and M for hours.
Oh, yeah.
Still good here?
Yes.
That one you need to retest.
I know. Like I feel like it's good for.
All right, can we talk about these? Since we're gonna go soon. The first one, you should do the ratio test. So this is similar to the one we did like earlier on today. So I would do my limit of, the absolute values here don't matter. Actually, well, they do matter in the middle one, but not in the other two. It is a n plus 1, so that's like so. And then times the reciprocal an will be like this. Like that, right? This is how we set up. I'm doing the ratio test for this first one. Actually, I believe you need to do the ratio test here. The root test is, it's hard to make sense of the nth root of the numerator in this one. Anyway, this, when I recombine terms, these 3's will cancel entirely. The 2's will cancel, leaving a 2 just on the bottom. The absolute values don't matter because everything's positive. And then the other part is n plus 1 to the 5 over n to the 5, which I'm going to write like this. N plus 1 over n to the 5. And then n plus 1 over n, when I take the limit, I'm going to get 1. For the same reasons as it always has today. So this lim just becomes 1/2. 1/2 being less than 1 means it converges. This is less than 1, so it is absolutely convergent. All right, I think everybody worked that out pretty well. Any questions about that one? Okay, the one in the middle, actually you can do with the ratio or the root, and just for more practice, let's try the one in the middle using the root test. So I'm gonna do 5 to the n over negative 2 to the n. because I see nth powers, I'm feeling like the root test might work. It doesn't work on that first one there because I do see an nth power here, but there's no nth power here, which makes the root test unwieldy on that one. But on this one, it's going to be great. So here, I'm going to do the root test. I make L equal lim the nth root of absolute value an. This is the only one in which the absolute value actually does matter. Nth root of 5 to the n over minus 2 to the n with absolute values. Can anybody say what's the effect of the absolute values here? Yeah? Right. It makes the negative 2 on the bottom into just 2 to the power n. And it has no effect on the numerator, 5 to the n. So this is just nth root of 5 to the n over 2 to the n. And what is the nth root of that? You can do this first, just to clarify, 5 over 2 to the n. And then the nth root cancels the nth power, and I just get 5 over 2. In fact, you don't even need to take the lim. The n's just cancel entirely. All right? That's because this one really it actually is a geometric series. In fact, you don't even need to do any of this. You can just say immediately the r is 5 over minus 2. But anyway, it is 5 over 2. This being greater than 1 means it diverges. All right. And then the last one. The last one, you must use the root test, I believe. I mean, I don't know. You might be able to make this happen using the ratio test, but it's certainly easier doing the root test. So this one, I'm going to do the root, and I go nth root of an. 5n plus 3 to the n over 2 to the 2n. Now, you have to think a little bit about how am I going to take the nth root on the bottom. On the top, it'll just be 5n plus 3 to the n. There are a few ways you could think this through. Maybe I'll just write out on the top 5n plus 3, right? But on the bottom, what I have is the nth root of 2 to the 2n. All right? You got a suggestion? Yeah, 2 to the 2n is the same as 2 to the 2n is the same as 2 to the 2 to the n, right? This is what happens with exponents inside of exponents. And that, of course, is 4 to the n. So you can write the bottom there as lim 5n plus 3 over nth root of 4 to the n, and that's just 4 on the bottom. All right, so this is how I would handle 2 to the 2n. Another suggestion, I don't know if you want more suggestions, but you could have also, from here, think of this. Remember, nth root is the same as the power 1 over n, just like the square root is the same as the 1/2 power. The nth root is the same as the 1 over n power. So this denominator you could write as 2 to the 2n to the power 1 over n. And then multiplying the exponents, this equals 2 to the 2. Which is 4, right? That's another way to arrive at 4 on the bottom here, if you prefer multiplying 1 over n exponent. Anyway, what is this limit? This is slightly weird, but this limit does not exist. When n goes to infinity here, you get infinity for this limit, all right? This limit goes to infinity. This is interpreted as, the thickness. As L being greater than 1. All right, this L is actually infinite. So I actually meant to write that in before. Would you mind scrolling up and writing in? This is true for the ratio and also the root test. Right here, if L greater than 1, as a little, even L equal infinity, that still counts as greater than 1. I think as I was walking around, this is how everybody interpreted this anyway. But it is possible that the L does not exist and equals infinity. That still counts as L being greater than 1, and it still diverges. All right, here ends the tests for convergence. So next time we will discuss power series, something different. See you then.